Well, it's a week since I was here before, and as I predicted, the numbers of flies have absolutely skyrocketed. They've gone through the roof. So I'm going to wear an all-in-one suit for a bit of protection this week. I reckon there could be as many as 10,000 flies inside. Because our box is sealed, they can't escape to find new sources of food and places to lay their eggs. I'm worried that their sheer numbers may disrupt the natural course of decay elsewhere in the box. Well, there are just now simply too many flies in here. It's becoming quite unpleasant. And it's causing a problem because of the fly speck. That's their excrement, which they leave on the surfaces, inside the glass, everywhere. So it's time I try to reduce them a little bit manually. The trouble is they're flying quite low and they're sitting on surfaces. It's actually very hard to get them. And the trouble is half the flies are actually drunk. Because over there in the fruit bowl, it's all become alcoholic in there. And the flies are actually flying under the influence at the moment, which is probably why there's so many of them on the floor. You can hear them. It's like a sort of constant buzz. This is pretty unpleasant, I gotta say. Whoa! Woohoo! Look at this. It's no wonder that flies are so hard to capture. Their compound eyes give them 360-degree vision, so they can respond to movement in less than 30 milliseconds. Me and my net can only do so much. It will be hunger that kills off these flies in the remaining few weeks as their food supplies in the box run out. Their role in our project is coming to an end. We should start to see other insects moving in to carry on the process of breaking down what's left of the meat. In the meantime, the fly's need for food is affecting one of our other agents of decay. Six weeks in, and mold is still ravaging the sandwich box. It's even grown out from under the lid, and it's attracted the attention of our starving flies. Now, this to me, Patrick, is one of the most amazing things I've ever seen. I mean, Patrick Hickey has returned to investigate what's been happening to the molds in our house. How many actual species of fungus are here?
Oh, at least 20 or 30, maybe more. Maybe
20 or 30 species of fungus? I just can't wait to have a sort of...
It's the perfect environment. I mean, some of those actually are fairly dangerous. I mean, one of the ones there, one of the molds here, Aspergillus flavus, which is a kind of greeny yellow one, can produce quite nasty toxins, so you certainly want to be careful.
I see. But look at this, look at that. I mean, it's a solid mat.
Oh, yeah. Yeah. Oh,
now, there are the layers of sandwich. And it's all the way through, it's completely through. Now, there aren't any flies here, of course.
Yeah, well, it was sealed in the box, so the flies couldn't get in. Big contrast there to the fruit bowl, which was left open, and a couple of weeks ago was really covered in thick layers of fungus.
Look at the fly. Look.
And the flies have stripped it bare. I mean, the flies have gone in there, they've been eating the fungus, they've been eating the spores, and really just recycling the fungi.
So fruit has become mold, mold has become flies. Flies are flying off somewhere else, and if they were outside, they'd be eaten by something. Outside in the garden, other forms of fungi rely on insects to help them do their job. This is the fruiting body of a stinkhorn fungus. The rest of the fungus is below ground, feeding on wood and plant matter in the soil. These stalks emerge when the fungus is ready to fruit, growing up to 15 centimeters in less than 24 hours. When they break through the top layer of soil, they release an intense smell that flies find irresistible. The smell of dead and decaying meat. The flies strip the jelly-like flesh from the mushroom and help spread its spores. Even after 30 years of studying biology, I'm still amazed by the complex behavior of these simple organisms. But stinkhorns aren't the strangest things feeding on the decaying wood in our garden. Hidden away in our woodpile is something even more intriguing. This is a slime mold. It's the largest single-celled organism on Earth, and it can grow to more than 3 square meters. Scientists have recently discovered that these primitive life forms have some rather sophisticated talents. At Oxford University, Dr. Mark Fricker is one of a team of botanists and computer scientists studying a species of slime mold called Physarum polycephalum. For years, slime molds have fascinated scientists with their remarkable ability to solve simple mazes. Put food at the end of a maze, and the slime mold will find the quickest route through. But scientists started to wonder if the mold could do more than just perform clever tricks.
You can set them lots of little tasks, and you can allow them to forage and connect up little food sources to see what sort of network they would make.
Okay.
And a geometric shape, so a square or something more complicated, is interesting, but we wanted to see whether they would be able to solve a slightly more complex problem.
Mark is recreating an experiment he worked on with colleagues at Tokyo University. He takes a blob of slime mold and then surrounds it with a pattern of oat flakes, an irresistible treat to the slime mold. What happens next is recorded by a time-lapse camera. The slime mold locates the oat flakes by growing out in all directions. But within hours, the slime mold shrinks back, leaving an intricate web of tubes that connect the oat flakes. It's these tubes that transfer nutrients around the slime mold. Incredibly, everything you can see is part of one single cell.
It needs to build a network that's quite efficient to transport all those resources around. At the same time, that network mustn't cost too much. It mustn't take up too many of its own resources. And then the other problem it has is it's going to be subject to damage. And so if there was only ever one connection, there's a risk that that would break.
The slime mold takes no chances. It grows backup routes to make sure that its food supply isn't cut off. But there's something even more extraordinary about what the slime mold has done. Mark hasn't just laid out the flakes in a random pattern.
The large blob in the middle is Tokyo.
Right.
And each of these food sources is positioned as one of the cities nearby Tokyo.
So it's a recreation of the area around Tokyo.
Indeed. So this is actually what it's based on. This is the rail network around Tokyo. And we can superimpose that over. Okay, so we can align
That's
it up.
identical. It's absolutely identical.
So you see a lot of these connections, it's formed the same sort of links. It's got a few extra ones in as well. It's a slightly more resilient network than the ones that the engineers designed.
You're telling me, wait a minute, that this slime mold has built a better network
A remarkably
than
similar
the humans
network.
built.
Yes.
And the Tokyo rail system is one of the most efficient and well organized in the world. It took lots of skilled engineers using lots of brain power to plan it. Yet somehow, slime mold has achieved the same goal: how to efficiently link together multiple locations. Slime mold has also been put to work in other parts of the world. Here it tackles some of Britain's major motorways. And this is its take on the best routes around Spain. And here are some interesting alternatives to America's Route 66. what is the slime mold actually displaying here?
It's a sort of smart behaviour. It hasn't got a brain, it hasn't got a nervous system, but it still seems to be able to solve these sorts of complex problems with very simple rules. And that's something that the computer scientists that we're working with are getting very interested in, and whether or not you can take inspiration from this system and apply it to other sorts of problems.
So how does one of the most simple life forms on Earth, a single-celled amoeba that spends most of its time on woodland waste, match its wits against transport engineers and computer scientists? The clue seems to lie in its extraordinary biology. Professor Bruce Ing is a self-confessed slime mold obsessive. He's going to help me track down some slime mold in one of its native habitats. So slime molds are not rare things, are they?
No, no, they're very common indeed everywhere.
But overlooked.
Overlooked because they're shy, not easy to find unless you know where to look and how to
Shy
look.
slime mold.
Shy slime mold, yeah. Do you remember seeing the film The Blob?
Yes.
A giant mass of jelly eating caravans.
It was a slime mold,
It was a slime mold.
but not one we'll find
But-
here.
Not
I
as
hope.
big as that, I hope.
Bruce's 54 years in the field prove vital as we hunt the elusive slime mold. After half an hour, he finds what we're looking for. Not quite a sheet I was hoping for.
No, indeed not, but still
It's
the
there.
real McCoy.
Yeah. This small patch of orange is creeping slime mold. Up close, you can see how it's constantly pulsating. When one part of it finds something it likes to eat, it pulses more rapidly. Scientists believe that it's this pulsing that helps transmit information across the entire cell, allowing the slime mold to move towards its food source. These pulsations control where and how they grow across the forest floor, or even around the oat flakes of the Tokyo rail map. What's so special about slime mold is that it can use this information to make multiple decisions simultaneously. Pretty ingenious stuff for a single-celled organism. Slime molds are what's known as self-organizing systems. It's not a unique phenomenon in nature. Flocks of birds work in a similar way. With no leader, no overall control, the flock nevertheless acts as a single unit. But slime molds can do something that flocks of birds could never do. Meet the Phibot, the world's first slime mold-controlled robot. The Phibot is the brainchild of Dr. Soichiro Tuda and Dr. Klaus-Peter Zauner from Southampton University. Their robot takes its orders from a tiny blob of slime mold. I sort of don't believe you. I want to see, I want to see it working. Prove it.
All right. Flip the switch. So let's
It,
spit
it
it out.
just seems almost unbelievable. It's not instant, is it? It's not sort of instant. Oh. Wow. That's fantastic. The slime mold sits on an electronic chip inside the robot. As it transmits information around its single cell by pulsing, the robot detects these pulses and translates them into much larger movements across the surface of the table. How did you get the idea for having a live organism inside a robot?
One inspiration source, obviously, from the Daleks, from Doctor Who.
This is inspired by a Dalek.
Yes.
So it's the same thing, isn't it?
Yeah, exactly.
You've got a live organism in the machine which controls it. The Flybot is pioneering a new approach to computing. Today's computers use a single central processing unit to do their thinking. But the slime mold has no need to ask a brain what to do. All parts of the cell just work together for the good of the whole.
That simple organism inside processes information in a completely radically different way from our conventional computing technology. So we want to learn more how it can do that information processing.
So slime mold could hold the secret to a revolution in computing, or even the creation of artificial intelligence. Not bad for something you can find in your wood pile. There's only a week left to go in our project to study decay in a typical house and garden. The pace of change in the box is beginning to slow down. But even now, decay is following an ordered sequence. What one decomposer leaves behind is food for others. Well, it's day 44, and the one thing that's immediately obvious is it doesn't smell nearly as bad in here as it did. It's quite pleasant. The other thing that's obvious is there are very few flies now. The majority of the flies that hatched out have died. There aren't as many dead ones lying about as I expected, but it looks as if a few flies have got themselves stuck in this bottle of wine, as they've obviously been searching for something to drink. This is solid. Look at this. Oh my God. That is incredible. I can't get them all out. I've never seen so many flies in one bottle in my life. I can barely get them out. That sort of explains why I wasn't seeing as many flies flying around as I expected. It's because most of them were in here. Look at it. It's just incredible. It's thick. That's thick flies. Look at that. Conditions in the box are very dry. All that remains of the meat are hardened chunks of sinew and skin. Even if the flies had survived, there's nothing left for another generation of maggots to feed on. But this is the perfect fodder for beetles. This dried meat gives off a far less pungent odour, but the smell it does produce gives them a signal that starts the next stage in decay. Decay happens in a series of waves, so even with this fish, which is now dry and hard, there are beetle larvae who will eat this, so there isn't anything wasted, and that's what I'm hunting for now. I'm hunting for the larvae of a larder beetle, and there is one right there. Larder beetle larvae are present in around half of all homes. They only colonize a carcass once it's become dried and desiccated. Their powerful jaws allow them to eat through flesh, hair and skin, and they can strip an animal down to the bone. This stage in decay moves slowly though. Larder beetle larvae take months to pupate into these adults. The job of recycling what remains in the box could take generations of them, years to complete. But another beetle in our box does allow us to see how effective these insects can be. "36 days ago, 2 sexton beetles took less than 12 hours to bury our dead rat. What I'm aching to do now is a spot of archaeology, because what's happened is the sexton beetles have taken the rat down and they will have formed it into a ball on which their larvae have fed, and hopefully for 36 days should be enough time. I should find a crypt in which the rat sits, surrounded by its own fur, which they've smeared on the outside, and there should just be bones left. So this is this for me is about as exciting as it gets. So I'm just going to use a hoover to gently take away the soil. What is amazing about these insects is that they're one of the very, very few insects who look after their young. They actually take care of the young. So once they've dragged the prey down and hidden it underground, they will lay the eggs around the crypt, if you like, and then the larvae will move in and feed, and they'll help them to feed as well. So now we're beginning to see a shape here. Oh, this is very exciting. Turn that off. Now, I wonder if I can just free it. There it is. Now that is just fantastic. And there, look at that. That's all that remains there of that rat. You can just see the top part of the skull there, and the teeth, and the rest of it has completely disappeared. There is nothing left of that rat. We're now at week 8. We're nearing the end of our project. But there's one final stage of decay I want to investigate, and it's probably the most important. We've watched as the nutrients locked up in plant and animal remains have been reused by other organisms. In the process, complex things like chickens, rats, and fruit have become simpler ones: insects, fungi, bacteria. But the true power of decay is its ability to reduce complex things right back to the most basic building blocks of life. And all through the project, that's been quietly happening in a corner of the box. This is one of the best places to see decay in action. Now, we set this up 8 weeks ago, and it was piled to the top with plant material. It's now completely decayed down. We've been adding to it. And what I really want to do now is to just have a good look inside and see what's going on. Now, decay has been happening here, and the further you go down, the more advanced it is. Oh, there's a snail on my trowel handle. As all gardeners know, compost heaps turn dead plants into a form of nutrients that new plants can use. On the surface, animals like snails, slugs, and worms begin the process by eating the remains of plants, helping to break them into smaller pieces. The waste they excrete and anything else left behind is eaten by even smaller creatures like these mites, too tiny to be seen with the naked eye. And this process continues down through the compost, ever smaller organisms reducing the plant waste to ever smaller components, until tiny fungi and bacteria are able to break down the very cells of the plant. A teaspoon of soil contains 4 billion microorganisms. They finally release the nitrogen and other building blocks of organic life back into the soil. What we end up with is an incredibly fine soil, which is the result of the breakdown processes of countless organisms. So having begun with a big pile of green material, you may think that that is an end point, but it's not. It's just the beginning. From here, life can begin to rebuild. To me, this is the most amazing moment in the story of decay. When we began 8 weeks ago, we wanted to demonstrate its significance in a unique way. This is probably one of the most important experiments that we've set up in the box. And these may look like ordinary plants, but they're going to show us a part of the story that's absolutely crucial. These are the marigolds and radish seedlings I planted back at the beginning of the project. They've flourished into mature plants. I've been feeding them with a special liquid compost made from plants grown using chemically labeled nitrogen atoms. If everything has gone according to plan, we should be able to track how individual atoms of nitrogen are transferred from the mustard plant to our seedlings. From death to life. We sent samples of our plants to Professor Malcolm Clench. It's time to find out if our experiment has worked.
First one is from the marigold.
Right.
So what you can see at the moment is just a photograph of the marigold leaves themselves. Yeah, that's right.
He's able to pinpoint exactly where the labeled nitrogen has ended up.
Now let's start to play through the little video clip. We'll come up with an overlay that shows the nitrogen in high abundance.
That is really clear.
Yes, it is very clear, isn't it?
Each one of these dots shows where we found traces of the labeled nitrogen from the mustard plant in our marigold leaf. White areas show where it's concentrated. How can we be 100% sure that that labeled nitrogen has come from our experiment and not from anywhere else?
Well, the form of nitrogen that we're using, nitrogen 15, is only 0.3% naturally abundant. And we can see here areas of high intensity, and they can only have come from the mustard, which was grown just with the labelled nitrogen in.
So that is the definitive proof positive
that we've got
of the cycle of life.
Indeed.
Right there on the screen.
Indeed. I think you're going to be really pleased with the radish results. We can see first off
A very nice radish.
a very nice radish, one that you prepared earlier. As if by
Wow,
magic.
look at that. That is absolutely cast iron proof that we have transferred
Yep.
material, an element in this case,
Yes.
from one organism, one plant that was dead and decayed, fed to something else, and it takes it up.
It's incontrovertible.
This is what I hoped we'd see when we began our project. It's the fundamental principle of decay revealed in front of our eyes. For me, this is as good as it gets. 2 months of decay have transformed the Afterlife box. Little is left of the fresh food we began with. And what remains will continue its inexorable journey back to the basic building blocks of life. But as our plant experiment so dramatically demonstrated, what we have witnessed in the box is a process of renewal that we are all part of.
It's a real sort of a snapshot of everyone's life, and to see things changing as they do is a fantastic experiment.
We'd be in a horrible mess if we didn't have decay. When you see what nature can do to get rid of all the dead things in the world.
We need that decay to happen in order for life to go on, I guess.
We tend to think of life as a linear process with a beginning and an end. Things go from life to death. But I hope the box has shown this process in a new light. Life is an ever-repeating cycle, one that's not just happening here, but everywhere on the planet. The plants and animals of Earth's ecosystems rely on this continuing cycle. Even the atoms that make us up are recycled. They come from the food we eat, the air we breathe. They're in our flesh, blood, and bones. They've been used millions of times before, and they'll be used millions of times again.
A moral conundrum in Dinner with Portillo here on BBC4 this evening at 11:30. But first, Andrew Graham Dixon explores the ancient tradition of the religious relic and its attendant story of persecution, faith and hope. Treasures of Heaven is next.
Five, 3, 2, 1.